Good morning, Dr. Anand. Today we would like to present our operating system presentations. Our group name Oasis consists of 5 students, including me, Leonal, Sigar, ANAK, JAME, with matrix number 75402. Our project main topic is scheduling algorithm of round robin for the use of Unimass Web. Round robin is one of the best algorithm to suit the job for Unimass Web. The main aim of CPU scheduling algorithm is to minimize the waiting time, response time, turnaround time, overhead, and context switching, and to maximize the CPU utilizations. In the round-robin CPU scheduling algorithm, the performance of CPU depends on the selections of time quantum in a time-shared system. Hence, in these presentations, we will discuss on which quantum time is the best. Without further ado, let's proceed to our next member.
Hi, I'm William. Now I will explain about the coding of our program. In this project, we use the C++ programming language to evaluate the round-robin scheduling algorithm. This program will show the turnaround time and waiting time of the process in job list 4 and calculate the average turnaround time, the average waiting time, and the number of interrupts of the 30 processes in job list 4. Actually, it is quite understandable to use some header files in a C++ program and also the variable declaration. So I will not go too detail with it. Simply to say, we apply the header file, include IO, include vector, and include fstream for this program. And also we declare some important variables to use for the program. There are some important parts that I would like to mention for the coding part. The first one is that we created a file named joblist.txt to read the arrival time and the burst time of all the processes in job list 4. The second part is the detail of the files. In the joblist.txt file, there are 30 jobs with different arrival times and burst times. The program reads all the assigned arrival times and burst times of each job for processing. The file starts with the arrival time, then burst time of the first process in job list 4, then followed by the arrival time, then burst time of the second process in job list 4. It continues until the 30 process of the job list 4. The third part that I would like to mention is creating algorithm. Here, we're creating the algorithm to calculate the turnaround time, the waiting time, and the number of interrupts for the job list 4. And lastly, the fourth part, print out the results, where we print out the average turnaround time, the average waiting time, and the number of interrupts of the 30 processes in the job list 4. Okay, this is how our full programs looks like. So now I will show you a demo for our program. Okay, the first thing we will see when we run the program is that it will ask us to type in the time quantum. So now we take 5 as the time quantum. Okay, now we can see the results. It will show the turnaround time and also the waiting time of each process in job list 4. Okay, at the last part of the program, you will see the average waiting time, average turnaround time, and the number of interrupts of the process. So basically, this is for the coding part.
This is the outcome implemented from the program. We test all the related quantum time and record the result of average turnaround time, average waiting time, and number of interrupts in a table for analysis and synthesis of the best quantum time for juries 4. Then, we use bar chart to show the result. The first bar chart shows the graphical analysis of average turnaround time varies with their quantum time respectively. We observe that the quantum time equal to 15 milliseconds is the shortest average turnaround time, while the quantum time equal to 50 milliseconds is the longest average turnaround time. Turnaround time should be minimized to avoid any excessive delay in the scheduling process. Therefore, Based on the performance of the average turnaround time, the most suitable quantum time for job list 4 is 15 milliseconds.
The second is the waiting time of the jobs. The bar chart shows the overall analysis of average waiting time varies with the quantum time respectively. As one diagram, we can observe that the reverse result of the average waiting time for the job is 16682.6 when the quantum time is 15 milliseconds. But the best result of the average waiting time of the job is 16527, while the quantum time is at 16 milliseconds. Due to waiting time, we are ready respond while waiting to getting the CPU in the round-robin scheduling. Hence, that's the performance of the average waiting time. The most suitable quantum time for job list 4 is 15 milliseconds. The third is the number of interrupts. The bar chart shows the graphical analysis of the number of interrupts in terms varies with the quantum time respectively. The number of interrupts is equivalent to the number of contents switching that occur in the job list 4. Based on the bar chart, the 5 millisecond quantum time has the higher number of interrupts, which is Q929. The lower number of interrupts is Q39, the quantum time for 16 milliseconds. The high amount of contents switching should be minimized before it slows down the execution of the jobs, so that the number gradually increases without in less throughput. Therefore, based on the bar chart above, the most suitable quantum time for job list 4 is 16 milliseconds.
Thank you for the presentation from HOOI-san. My name is Kai. Now I'm going to talk about the most suitable quantum time for job list 4 supplied by the client. There are 3 performance metrics that need to be considered while evaluating the most suitable quantum time. They are the turnaround time of the jobs, waiting time of the jobs, and the number of interrupts. If according to the explanation of average turnaround time and average waiting time for my group members, the most suitable quantum time is 50 milliseconds because they both have the lowest average turnaround time and average waiting time, respectively, for job list 4. The turnaround time and waiting time shall be minimized to avoid any excessive delay in the round-robin scheduling process. But the difference between the average turnaround time and waiting time for 50 milliseconds and 60 milliseconds quantum time is not that big, with a 25.3 average turnaround time and 25.4 average waiting time as shown in the table. So, we can turn our attention to the number of interrupts to decide the most suitable quantum time. For the number of interrupts, 60 milliseconds quantum time is the smallest among all the quantum time, which is 339. An optimal quantum time with a minimum number of interrupts is important because it leads to fewer overheads, which will result in more throughput. A high throughput is good for the round-robin scheduling algorithm to maximize the number of processes that complete the execution per time unit. So, the CPU will not be idle and keep busy 100% of the time with useful work. In conclusion, we think 60 milliseconds might be the most suitable quantum time for job list 4. That's all from us. Thank you for listening. Bye-bye.